Awesome. Okay. So, cool. All right. So let's talk a little bit about exam 4. So exam 4, that will happen the 29th. Right. So I got a couple of people here between different cohorts. You guys kind of know how it rolls, right? Starts right at class, 75 minutes, etc. And then, oh, actually, yeah, you guys want to see what I'm writing? That might help. Sorry. So yeah, a couple different cohorts here, but whatever time class starts, that'll be when the exam is. In terms of topics, you're looking at hemo-phys, hemopatho. Oh, come on. Patho. GI-phys and GI-patho. Okay. So those will be kind of the 4 topics there. In terms of the actual exam itself, I'm thinking maybe give or take about 35 multiple choice, maybe 5 kind of short answer, fill in the blank. And 1 essay. Okay. All right. So in terms of, so that's kind of what you're looking for forward there. But that'll be the last big hurrah for exam 4. Any questions about exam 4, what to expect? I would say the things to help you out, flashcards for the anemias. You have your table for your GI phys, and then as you're going through the pathos for GI patho, put those pathos into the table, just put the names in there. And if you can't explain it, then that's the one you need to brush up on. But hopefully that kind of gives you a good outline for this stuff here. Okay. All right. Cool. So today we are going to jump into renal phys. Now, renal can be a mixed bag. Some people like it, some people don't. It can be overly complicated, yet it can be pretty simple. I would say the thing that kind of trips students up a lot here, don't get lost in the weeds. You need to maintain the overall bigger picture to see where things fit in, kind of like immunology. Okay. Also, to kind of give a little bit of weight of this, exam 5 will just be renal phys, renal patho. That's it. So exam 5 is shorter. So technically this lecture makes up 50% of exam 5. Okay. All right. So here is kind of like an overview. This is the table of contents. This is what we're going to get into today. First part of the urinary system we're going to run through is the anatomy. Pretty straightforward on this one, right? Ureter. This is the tube that's going to connect kidneys to the bladder. Okay. Your urinary bladder. 3 guesses. What do you think the urinary bladder does? Hopefully it's doing it for you right now.
Urine?
Yeah, exactly. That's perfect. Holds urine. Okay. The urethra, that's another tube. This is going to connect the bladder to the environment. Okay. And then your kidney. Kidney filters your blood, yes? Ish. Your kidney has three very important functions here. Your kidney filters. So I'm going to say filters. It reabsorbs and it secretes. Okay. So a heads up, where your heart has one job to pump blood, your kidney actually has three. Okay. So running into those functions, the second and third part of the lecture will be about the physiology, the actual function. So these steps here, step one is filtration. Now I know this is going to sound very kind of grade school-esque, but if you can keep these in mind, it's going to keep you organized, okay? Filtration, that's when we take stuff from the blood and put it into the urine. Reabsorption is the opposite way. So reabsorption is when we take stuff from the urine and put it back into the blood. Secretion is finally blood back to the urine. Okay. Then the regulation of urine volume, that's hormonal stuff. We'll get to that at the end. Okay. So again, just really impressing upon you guys, the meat and potatoes is going to be here. This is give or take about 80% of today's lecture. Okay. While again, the anatomy, it's going to be really brief. It's like 20%. And then renal here, I lied. 10%, because the regulation of urine volume, that makes up the last 10%. Okay, so just heads up, the physiology is going to be the biggest thing there. All right, so here is the anatomy for your kidneys, pretty straightforward. Let's do a little bit of kind of open guessing here. What is the most common cause for a UTI? I.e., what microorganism is the most common cause for a UTI, urinary tract infection?
E. coli.
Nice, it's E. coli, very good. And we'll elaborate on that, but just to let you guys know, E. coli is right there. Okay. How about what is the most, or what, sorry, what are most kidney stones made of? Or most, nice, yeah. Calcium. Most kidney stones are made up of calcium. Okay, so that's your urinary tract, a little bit of patho there. Here is your urinary tract in color. Cool, cool. All right, so now looking a little bit closer here, looking at the bladder, a couple of things I need to point out is your bladder is made of detrusor muscle. The detrusor. Okay, so your bladder is made up of this muscle. Does anybody know what kind of muscle it is? Skeletal, cardiac, smooth?
Smooth muscle.
It's going to be smooth muscle. I.e., it's going to be involuntary. Okay, so if I activate my parasympathetic nervous system, what would that do to my bladder? If I activate my parasympathetic nervous system, what would that do to my bladder?
I would want to go to the bathroom.
It's going to contract, absolutely, driving you to urinate. So be careful there. If you activate rest and digest, that's going to make you urinate. Okay. Next up is the trigony. So trigony is kind of like this area right here. Trigony. This is the most common area to be inflamed during a UTI. Okay, i.e., if somebody has a urinary tract infection, the trigony is the most common or most likely area to become red, inflamed. Okay, so if someone's trigony is inflamed, that probably indicates a UTI. Next up is the internal urethral sphincter. Now, if you guys notice, your internal urethral sphincter is just an extension of your detrusor. Therefore, your internal urethral sphincter, is this voluntary or involuntary?
Involuntary.
Perfect. So according to this, your bladder is involuntary, your sphincter is involuntary. Can you hold your pee? When Mother Nature starts calling, okay, I hope you guys can hold your pee. I hope. But if your bladder starts contracting, there's no way to stop it. So how do you hold your pee? Your external urethral sphincter. So if you can voluntarily hold your pee, what kind of muscle is your external urethral sphincter?
Voluntary.
Voluntary, i.e. skeletal. Okay. So think about babies. Babies, they pee all over the bloody place. Why? Because they don't have great control of their skeletal muscle. They haven't learned how to contract it yet. Who else doesn't have great control over their skeletal muscle?
Old people.
Yeah. So when we get a little bit older, all of us get to look forward to being careful when we laugh too hard or when we sneeze too hard. So medical term for where the kidneys are located, I'm just going to tell you, retroperitoneal. Okay. All right, so taking a look, slice through the kidney. This is talking about the flow of urine. Okay, now a little bit of vocabulary here. Some people are big about like it's filtrate and then it's urine. I just call it all urine. Okay, so I don't really separate them out by concentration. So just heads up, I'm just gonna call it urine. Okay, so blood comes into the renal artery all the way to the outer edge. So the outer layer is going to be the cortex. This is the cortex. So we kind of start here. Okay, so blood goes all the way to the outer layer. From the cortex, we enter these little, I don't know, fin looking things. This is the renal medulla, also known as the renal pyramid. Renal pyramid. From the renal pyramid, we're going to enter this area. Notice these little sharp corners on the side here. These sharp corners, I'm hinting at something. They are actually pretty jagged. These little jagged corners are called the minor calyces. Minor calyces. From the minor calyces, we're going to get into the bigger part here. That is your major calyx. From the major calyx, we finally enter this area right here. This is the renal pelvis. Then we finally enter the ureter. Okay. So those are just the general structures. The reason why you need to know about it is we're going to start talking about obstructions with the pathos. So if I talk about an obstruction in the renal pelvis, you should kind of know where that's at. Okay. All right, so here we're taking a little bit of a closer look. So this outer layer right here, this is your cortex. This is that outer kind of ridge, and then your medulla. What I want you guys to notice is that your medulla is made up of these loops. There's all these loops inside your medulla. Does anybody remember what these loops are called?
Oh, the loop of Henle.
Nice. Medulla made of loops of Henle. Nice work. Okay. Now the thing about the loops of Henle, the longer the loop, the more concentrated urine becomes. So the longer the loop of Henle, the more concentrated your urine becomes. Taking a look at this here, notice we have like a long loop here. We got a short loop here. Because it's built like a pyramid, question, which one do you have more of? Short loops or long loops? And think that it's built like a pyramid.
Long loops.
Actually, I wish. We only have a few that can go all the way down. Most of them sit up here. Okay, so what I'm getting at is we mostly have short loops. So as humans, are we good at concentrating our urine? Oh God, we're terrible at it. We're terrible at it. On the other end of the spectrum, fun fact, camels. Camels are so good at concentrating their urine, it can come out as a gel. Okay, all right. So this right here is your nephron in yellow. Notice your nephron is entangled with this capillary. Sorry, Lita, that's this whole quarter. Notice that your nephron is surrounded by this capillary. This is why we can constantly transfer things between urine and blood. If you remember at the beginning, filtration was like blood to urine, urine back to blood, back to the blood, or back to the urine. So kind of keep that in mind. All right, so your nephron, it's a functional unit. You don't need to know that number, just saying like, hey, you have a lot of them. Cortical nephrons, their job is to make quote unquote normal / typical urine. Juxtamedullary, these ones make concentrated urine. So therefore, which one do you have more of?
The cortical ones.
Nice. You have more cortical nephrons. All right, so now we're going to be diving into the anatomy of the nephron. We have the renal corpuscle. This is the filtration unit. So this is where filtration happens. Glomerulus. Glomerulus translates to ball of yarn. Glomerulus translates to ball of yarn because it looks like a ball of yarn. It's this ball of capillaries. Okay. So I'm going to say it's tangled capillaries. The tangled capillary. Okay. Your Bowman's capsule, this thing surrounds the glomerulus. Catches or surrounds the glomerulus, and it catches the urine out of the glomerulus. In terms of an analogy, your glomerulus, this is like a colander. I don't know if that's how you spell it. You guys know what a colander is, right? Okay. I did spell it right. Oh no, I had one extra L. Damn it. There we go. So your glomerulus is the colander. So I want you to imagine you had a colander full of, I don't know, kale, because for some weird reason you like kale. You have the kale in your colander. That represents your blood. You want to keep the kale out of the sink. The Bowman's capsule. This is your sink. So as you run water through your kale, through your colander, your glomerulus, that water comes out. That water is urine. Okay, so your colander sits inside of your sink. All right, so taking a look at this here, that thing surrounding it, that is your colander, that's your Bowman's capsule. Notice your ball of yarn right here, that is your glomerulus. Two structures I want to point out here is your afferent arteriole and your efferent arteriole. Now notice they are arterioles. Eels, what do you know about them?
Smooth muscle?
They have smooth muscle. We can change their diameter. Absolutely. Your afferent arteriole brings blood to the glomerulus. Your efferent arteriole drains blood away from the glomerulus. Okay. Afferent towards, to be, affectionate towards your center. Efferent is away. Okay. So if you're taking a look on the left here, the entire nephron is this thing right here. What we have been talking about is just that unit. That's the filtration unit. That's the renal corpuscle. Notice you have a blood vessel going in and a blood vessel coming out. So here's a nice little 3D rendering. So again, here is your glomerulus. That is your colander. Things are going to go, so blood will go in the afferent, and then things are going to come out. What kind of things come out of your blood?
Like waste or like vitamins and
Yeah.
shit.
So what happens is when we filter, basically everything leaves my blood. So kind of think of it this way. Your refrigerator. If you're going to clean your refrigerator, let's just say a weekly cleaning, how do you do it? Like we're not talking about like a huge overhaul. How would you clean your fridge?
Get rid of anything that's expired.
Yeah, you smell it. If it smells funky, you throw it away, right? Your kidneys, how they clean your blood, they take everything out of your refrigerator. They take everything out of your blood. That way I can choose what I want to put back. So when we filter stuff, we remove everything but large proteins. The large proteins stay in blood vessel. Okay. So you remove everything. That means water, electrolytes. Well, we'll go through this list here. I promise you don't need to write this down, but like water, electrolytes, glucose, everything just dumps out. What do we want to keep in our blood? Think about blood. What do you want to keep in your blood?
I mean, oxygen for starters. But like
What carries the oxygen?
the hemoglobin.
Yeah. Do you want to pee out blood? Does anybody fancy peeing blood? So guess what? You should probably keep your red blood cells in your blood. So your red blood cells with that hemoglobin, that's a large protein. Absolutely. You want to keep that in your blood. What other protein is in your blood that you probably don't want to pee out? Made by the liver.
Albumin.
Yeah. Do you want to pee out albumin? If you pee out albumin, that's going to lead to water balance issues. So albumin, red blood cells, white blood cells, platelets, we're going to keep that in our blood. Everything else, let it go. That's what I was talking about with that kind of colander, okay? So the question is, how do we do this? How does your colander work? Two ways. Step one, your basement membrane is negatively charged. Your basement membrane, i.e. the base of your colander, is negatively charged. So most proteins in your blood are also negatively charged. You put a negative next to a negative, what happens?
It repels.
Perfect. So your basement membrane, negatively charged, this repels proteins to stay in blood. Okay. The second method is your filtration slits, exactly as it sounds. These are like the little slits in your colander. These will limit the size of things allowed to pass. Okay. So take, for example, if somebody is peeing blood, what does that tell you about their colander? i.e. if you see kale in the sink, what does that tell you about your colander?
The holes are too big.
Yeah, someone has put a hole through my colander. It's maybe damaged. What if someone's not peeing anymore? No more fluid, i.e. you got your colander, you got your kale, you turn on the water, but nothing comes through your colander.
It's a blockage.
Yeah, you have a bowl, right? Very good. So that's a little bit of foreshadowing, but that's the idea there. I don't really care about this last one here. Okay. Next up is the juxtaglomerular apparatus. Juxtaglomerular apparatus. You may hear me just call it JG. It's a little bit easier. Anybody know what juxta means? Like a juxtaposition? Kind of means like para.
Isn't it like adjacent to?
Adjacent to, I'm going to say next to. Perfect. Glomerulus. So this is an apparatus right next to the glomerulus. Now there are two types of cells. These are cells at the JG apparatus. Your macula densa cells, their job is to detect change, particularly in pressure. So I'm going to scratch out this sodium bit. Okay, so your macula densa detect changes in pressure, i.e. your macula densa cells detect blood pressure changes. Okay. Your juxtaglomerular cells or your JG cells, these ones cause change. They cause change. So take, for example, renin. Renin, its job is to increase blood pressure. We'll explore that at the end. Why would I need to increase blood pressure? What state would I be in where I would need to increase my blood pressure?
Dehydrated?
Maybe I'm dehydrated. Absolutely. Maybe I'm dehydrated and I'm hypotensive. I have low blood pressure. Who detects that low blood pressure?
The macula densa.
The macula densa cells detect it, and your JG cells fix it. Okay. Another thing that your JG cells do is it can, actually, let me change this to blue. It can also do EPO secretion. So a little bit of a recap here. Why would your JG cells release EPO?
Hypoxia?
Nice. Hypoxia was the trigger. If I release EPO, that will increase red blood cell production because that hypoxia. Okay. Now, it's not actually accurate to say that your macula densa cells detected the hypoxia, but hey, I'm just trying to weave in previous material. Okay. So again, macula densa cells, their job is to detect. Excuse me, JG cells, their job is to cause change. Okay. So, boom, boom, boom. I don't really like this picture, so I'm going to skip it. The reason why is here's your afferent arterial, blood goes in. Here's your glomerulus, your colander. Okay, your efferent arterial draining. The new structure that we just talked about is your juxtaglomerular apparatus. Notice it is right between your afferent and your efferent arterial. That way your macula densa cells are constantly monitoring blood coming in. And JG cells, they can secrete things on the blood going in or out. Okay. So here are all the different structures. Heads up, I use a little bit of different vocabulary. The proximal tubule, I call the proximal convoluted tubule, i.e. the PCT. So just heads up, you're going to hear me say PCT a lot more than proximal convoluted tubule. Loop of Henle, we talked about. The distal tubule is the distal convoluted tubule, i.e. the DCT. And then the collecting duct, I just called it the collecting tubule. i.e. the CT. So just, sorry guys, hopefully some of you guys have seen PCT, DCT, CT. Hopefully that should ring a bell. That's just me being kind of old. Okay. All right, so let's do a little bit of an overview here. Now, if I were you, I'd probably do this on another sheet of paper where you have a little bit more room, just because this is going to be kind of your guiding path through this lecture. Okay. So talking about the nephron, you have a blood vessel coming in. And a blood vessel coming out. Okay. Blood vessel coming in, what was the name?
Afferent.
Nice. It was the afferent. Arterial. Blood vessel going out, therefore must be the efferent. Okay. And that crazy ball of yarn mess in the middle, what do we call that?
The glomerulus.
Yeah. Glomerulus. Awesome. Surrounding the glomerulus, you have the Bowman's capsule. Okay. After the Bowman's capsule, here we have PCT, proximal convoluted tubule. Then we got our loop. That's going to be your loop of Henle. Then you got your DCT, and then finally your CT. Okay. Now you remember how your nephron was surrounded by that capillary? It's actually the efferent. This turns into the capillary that follows your nephron. So that way we can constantly keep exchanging between the two. This capillary is called the peritubular capillary. Peri, around, tubular, around the tubular, around the tubule. Okay. So these are the structures here. That's the anatomy. Now we're going to get into the meat and potatoes with the physiology. So we're going to take a break. Promise I'm not going to steamroll into it. I would say what would be beneficial for you guys is get another blank piece of paper. And I would say 4 to 5 different colors if you can. Black is totally fine as a color, just to kind of help things out, help you with the diagram that's going to be coming up. Okay.
Hey, Brian, for break, can you just leave it on the last slide?
This one?
The one before it, sorry.
Yeah.
Thank you so much.
Yeah, and if anybody needs me to scroll back down, I'll be more than happy to. Let's say about 10 minutes here, so 9:05. We'll pick back up again. Okay. Awesome. Thanks, guys. Sorry about that. I don't like being an adult. I'm gonna go back. Give me chores and allowance. Shit. All right. So now we are jumping into the physiology. No, I never got an allowance. I just figure it's something that most people get that I can say that most people would relate to. All right. So physiology. So this is the big stuff here. This is the overview. Okay. So what I recommend, again, biggest thing here, keep things organized in which direction you're going from and to. So with filtration, that's when we're sending things from the blood into the urine. Okay. If you remember, we talked about filtration. The structure that was filtering was the glomerulus. The glomerulus is holding that blood and it's sending things into the sink, i.e. the Bowman's capsule. Okay, so what we just saw was filtration. We're going to go over it again. Then we have reabsorption. Reabsorption is when we go from the urine back into the blood. Because if you remember, everything left my blood. That can be a bit of a problem. I need to be able to put things back. So the structure that holds the urine is the PCT, and we're going to put it into the peritubular capillary. Okay. The final step, let's go orange, is secretion. Secretion is when we finally go from the blood back into the urine. That's going to be the peritubular capillary. And that's going to go into the DCT. So I know it sounds simple, but these three things here, this is what we're going to get into. There's some details with some of them, but if you can keep this in mind, this will keep you from being lost. Okay. And then the regulation of the urine volume, that's hormonal stuff. We're going to get into that. That's that final 10% here. Okay. All right. So filtration. I want you guys to think whenever you see the terms filtration, reabsorption, secretion, these are trigger words. These are keywords. That means we're moving stuff. Okay. So in the case of filtration, where are we going from and where are we going to?
From blood to urine.
Nice. From the blood to the urine. And what structure was holding the blood during filtration? What was the colander? What's the ball of yarn?
Glomerulus.
Nice. That's going to go into the structure holding the urine, which was the...
Bowman's capsule.
Got it. Sorry, I know I'm kind of like pulling teeth right now. You'll see why. Thank you. Okay, Bowman's capsule. So in filtration, we're removing everything out of the blood. So what do we filter out? Okay, so when I say filter out, that means I'm taking stuff out of the blood and putting it into the urine. Okay, again, that's kind of like a trigger word. Things that we remove: water, glucose, amino acids, and electrolytes. All of that gets filtered, i.e. all of the water in your blood goes into your Bowman's capsule. All of the glucose, amino acids, electrolytes, all of that goes into the Bowman's capsule. What stays behind in the glomerulus? What stays behind in your colander?
Blood cells.
Blood cells and?
Albumin.
Nice. And albumin, the large proteins. Absolutely. Okay. So this is a nice little view here. This is your glomerulus. This is your Bowman's capsule. Hey, you guys remember when we studied fluid balance? And I was like, hey, you should probably know these pressures because they're going to come back. You're back. Okay, so let's kind of do a little bit of a recap. So let's say that this structure here, okay, this structure is your glomerulus. And the structure surrounding it is your Bowman's capsule. Okay. Water wants to go from your glomerulus into your Bowman's capsule. So the equivalent of what we used to draw was that you had a capillary surrounded by this interstitial space, and water was being pushed out. Okay, so these are the same thing. Before we used to call it just a capillary pressure, but here we have a specific name for this capillary. What's the name of this capillary?
Peritubular.
The glomerulus, yeah. And before we used to call it just the interstitial space, but now we have a specific space, the Bowman's capsule. So a little bit of a recap here. What was the name of that pressure that pushed from the blood out into the interstitial space? What was the pressure that built up inside the capillary pushing water out?
Cap hydro.
Cap hydro. So before, you guys learned this as capillary hydrostatic. Now you just have a specific name. The name that we're talking about is the glomerular hydrostatic. Okay. So what I'm trying to say here, these are the same thing. These are the same thing. Before we learned about it all over the body, now we're learning about it just in the kidneys. If these are the same thing, what generates the glomerular hydrostatic pressure?
Blood pressure?
Blood pressure, absolutely. So taking a look at this diagram here, if I have hypertension, what happens to my glomerular hydrostatic pressure? Up or down? Goes up. Therefore, if I have hypertension, do I make more or less urine?
Less.
So if I have hypertension, that means pressure is building up inside of my capillary. It's going to push out more. So if I have hypertension, it would push out more. Therefore, would I be making more or less?
Or
Yeah. Okay. So that's your capillary hydrostatic. Now, if you remember, during filtration, what did we leave behind? What did we leave inside the capillary, inside the glomerulus?
blood cells and albumin
And what does protein and like albumin do?
pulls water.
Yeah. It's going to pull water. So before we learned this as your capillary oncotic, what would the name be now?
Glomerular oncotic.
Yeah, nice. Glomerular oncotic. Okay. So now looking at the other four, I'm probably not going to draw them completely out just because I don't have room. Didn't think about this one. Do you guys want me to draw out the capillary? Is that helping, or can I skip that? Draw it out? Okay. Thanks for not letting me be lazy. Okay, so you push on the wall and the wall's gonna push back on you. The wall's pushing back, okay? Again, before you learned that as the interstitial hydrostatic. But now we are in a specific space. So we're gonna call this capsular hydrostatic. Okay. Last one. Is if you had proteins in that interstitial space or proteins out here. Okay, so before we learned that as the interstitial oncotic. Okay, so how to kind of, so let me back up here. If we learned it as the interstitial oncotic because there's proteins in the interstitial space, where's that specific space now? What space has the proteins?
Capsular.
Capsular. So we're going to call this the capsular oncotic. Okay. Now, the question I have for you is talking about filtration. Filtration was defined as the movement from which fluid body to which fluid body?
Blood to urine.
Blood to urine. That's supposed to be in the middle. I kind of missed. So the question I have, glomerular hydrostatic. Glomerular hydrostatic. Does that help with filtration or oppose filtration?
It helps
Why?
because it's drawing water out
Out
Which
of
is
the
out of the
blood?
vessel.
Yeah, and we're putting it into the urine. So this helps filtration, i.e., it has a positive effect on filtration. It promotes filtration because, again, we're only talking about the direction in which water is flowing. So take a look at the glomerular oncotic then. Does that help or oppose filtration?
Oppose.
It opposes, absolutely. It has a negative effect on filtration. Capillary hydrostatic, what effect does that have on filtration, positive or negative?
Negative.
Negative, how'd you know?
Because it's pulling into the capillary.
Yeah, exactly. It's going the wrong way. Absolutely. And capsular oncotic, finally, what's that effect on filtration?
Positive.
Positive, because hey, we're going from the blood to the urine. Okay. Now, adding another layer to this onion. Your capsular oncotic pressure shouldn't technically exist. This does not exist in healthy people. Your capsular oncotic does not exist in healthy people. Why?
Protein shouldn't be outside of the glomerulus.
Very good. Proteins should not be filtered. Very good. If your glomerulus, if your colander is doing its job, it should keep proteins in the blood. If proteins are in the urine, there's a problem. So again, this is why it doesn't exist in healthy people. We'll explore that with pathos. But here's your little overview. If I increase filtration, does that mean more or less urine? If I increase filtration, do I make more or less urine?
More.
Because you have more water going from the blood to the urine. Okay. Now take, for example, I don't know, somebody has liver disease and they have less albumin. Which pressure would be affected by less albumin? Which pressure would be affected by less albumin?
Glomerular oncotic.
Yeah, glomerular oncotic, great. Patient has liver disease, they have less glomerular oncotic. Therefore, if someone is not making albumin, do they make more or less urine?
Less.
So again, just always draw the arrows. Always draw the arrows so that way you don't get confused, right? If this is our standard arrow, and now I make even less, sorry, the resolution's terrible. All right, let me back up. This is what we normally do. And if I have less albumin, I have less pulling. Therefore, do I have more water in my blood or my urine?
It's more in the urine, so you'll have more output.
So, is that another possible symptom of liver dysfunction? Less urine output? Yeah, it is. Okay. So what I'm getting at here is, just like we were talking before, if I'm talking about if you have an increase in a pressure, you have a decrease in a pressure, what's going to happen to urine output? Okay, just draw your arrows. Are we going from the blood to the urine or the urine to the blood? Make sense? Okay, so going back up here, I don't use these abbreviations. I actually really don't like them. I'll define them, but I won't use them. HP sub GC, that's your hydrostatic pressure at the glomerulus. Okay. Your OPGC, oncotic pressure at the glomerulus. Okay. Then your HPCS, this is your hydrostatic pressure at the capsule, Bowman's capsule. Okay. Now, if you notice, we're missing a force, we're missing a pressure. Which one are we missing?
The oncotic capsule one.
Yeah, we should not have our oncotic capsule, i.e. we should not have proteins in this space. If we have proteins, that's bad news bear. Now, if you notice, of the three pressures in a healthy patient, only one of them drives filtration. Only one of them promotes filtration. Which pressure drives filtration?
Glomerular hydrostatic.
Glomerular hydrostatic. Actually, let me do a little bit higher. Glomerular hydro is the only force for filtration. Again, with the caveat of a healthy person. So if your glomerular hydrostatic is the only force for filtration, the other two are working against it. Therefore, which has to be the largest force?
The glomerular hydrostatic.
Yeah, nice, nice, nice. So your glomerular hydrostatic, I'm just adding a caveat here, it has to be the largest pressure. Because again, it is the only pressure driving filtration. Okay. Another thing to note here is NFP, net filtration pressure. NFP must be positive. Your net filtration pressure must be positive, i.e., when you add up all of those pressures, it has to be positive. Why? Think about the net movement of water. Where do you want water going?
So it needs to be positive then, so that way you're creating urine output.
Exactly. It needs to be positive, so you're making urine. What if NFP equals 0? What if NFP equals 0? What does that mean? What does that mean for filtration?
You wouldn't be filtering at all, would you?
You would not be filtering. So if NFP was 0, that means 0 filtration, i.e., are you making urine? Now your kidney has 3 jobs: filtration, reabsorption, secretion. If NFP was 0, that means you have 0 filtration. Look at that, your kidney is not fulfilling a job. What do we call it when an organ is not doing its job?
Failure?
So if NFP was 0, that would indicate renal failure. Very good. Okay. Can NFP ever be negative? i.e., can you ever take urine and put it back into your blood? Not really. 0 is kind of the lowest as it gets. So I know this is a little bit of a crash course here with the fluids. Are we feeling okay? Again, you've already learned them. They just have a different name now. Okay. Right. So if you didn't like my pictures, that's fine. I have it in words. Your glomerular hydrostatic pressure, we talked about, that is positive. That helps drive filtration. It's based on your blood pressure. Glomerular osmotic, glomerular oncotic pressure, that is negative. Okay. Capsular hydrostatic pressure is negative. Your capsular osmotic oncotic pressure should be negligible in healthy people. Okay, again, that's if you don't have protein in your urine. But what if you did? What if someone did have protein in their urine? What if they did have a capsular osmotic oncotic pressure? Would that help or oppose filtration?
Help.
So if it did exist, it would be positive. Very good. And what do you guys need? And what do you guys know about NFP? Net filtration pressure?
Must be positive.
Perfect. Must be positive. All right. So talking about filtration, how do we measure this? As nurses, you're going to be familiar with GFR. This is, you're measuring glomerular filtration rate, i.e. how much fluid is a person filtering? Okay, so you're going to be very familiar with GFR. This is going to be one of the things you're going to learn about, you're going to see when you guys are out there. Basically, we're looking at how well are their kidneys filtering. Okay, so while NFP, your net filtration pressure, is the biggest determinant, you guys will measure GFR. What happens is GFR is directly proportional to NFP, but it can also be changed. So let me kind of give you an example. In terms of high blood pressure, in terms of high blood pressure, if somebody has hypertension, we talked about this, what will happen to your filtration rate? What will happen to your GFR?
It'll increase.
It'll increase. Very good. So if you have high blood pressure, this will, sorry, let me say, this will increase your GFR. High blood pressure, more blood to the kidneys, more filtration. Now the problem is GFR, we need to be constant. We need to be constant. i.e., hey, do you want to all of a sudden have to pee at 3 in the morning every day? You want to be able to make constant, a steady amount of urine throughout the day. You don't want spikes, right? So if I have hypertension, that spikes my GFR. What should be my goal? Should I increase or decrease my GFR?
Decrease.
Yeah, again, because I want it to be constant. Okay, how do I do that? I look at my afferent arterial and my efferent arterial. Now, remember how I kind of hinted at this. Arterioles, they have what?
Smooth muscle.
Smooth muscle. So that means I can change them. My afferent arterial, this is leading into the glomerulus. When I want to vasoconstrict or vasodilate, if my goal is to decrease filtration.
Vasodilate.
If I vasodilate, so I'm going to scroll back up here. If I vasodilate this sucker right here, is that going to let more blood or less blood into my glomerulus?
Okay, so you want to constrict it. Sorry.
There you go. No, you got it. You're good. That's why we're walking through it. Absolutely. You're good. You're good. Your afferent arterial, you need to vasoconstrict. Why? This will decrease blood into the glomerulus. If you have less blood, you have less filtration. That achieves our goal. Okay, your efferent arteriole always does the opposite. So if your afferent is vasoconstricting, you're going to vasodilate your efferent. Why? That drains blood out faster. If you drain blood faster, you can't filter it. Okay, so let's flip it. If I have a drop in blood pressure, my blood pressure tanks. What should my goal be?
To increase GFR.
Yeah, I need to increase it because if I have a drop in blood pressure, that tanks my GFR. So my goal to be keeping it constant is to increase GFR. Therefore, your afferent vasodilate or vasoconstrict?
Vasodilate.
Yeah, and how will that help? If I vasodilate my afferent arteriole, how will that help increase GFR?
Allows more blood in.
Nice, allows more blood into the glomerulus, more filtration, perfect. Efferent will vasoconstrict. Okay. All right, so that is filtration, step 1 of 3. You guys see what I'm talking about? Like, there are going to be some crazy details. So what I recommend here, don't write this down. I would say leave this slide blank. You'll see why. Okay, I promise. So taking a look here at our nephron again, I would say just use this couple minutes here as an opportunity just to kind of review things in your head. Okay. I promise I'm not going to leave you stranded. So we just talked about filtration. That happens right here. Filtration. We're going from what fluid to what fluid?
Blood to urine.
Nice, blood to urine. And what structures are involved? What structure holds the blood? What structure holds the urine?
The glomerulus and the Bowman's capsule.
Nice. Glomerulus to the Bowman's. Okay. And the things that we filter out of our blood, 4 things: water, amino acids, glucose, and electrolytes. Okay. Within that little space right there, you know you have your pressures, your fluid pressures, right? This is the overview. Don't worry about it yet. I promise I'm not going to leave you hanging. Okay. So that was filtration. Do you guys need a break before we go to reabsorption? I'll give you guys a heads up on this one too. It gets easier. Filtration is the hardest one. Secretion is by far the easiest one. Okay. So reabsorption is still a little bit wonky, but let's take a quick little break, kind of get some blood going here. So how about like 10 o'clock or not 10 o'clock, 9:50? We pick back up again? Okay. All right. Whew. Almost past the thick of it, I promise. Whew. Okay, so reabsorption. Okay. Going back to the basics here. Reabsorption, we're going from the urine back to the blood. Okay, urine back to the blood, i.e. from the PCT to the peritubular capillary. Okay. So again, putting things back into the blood. What do you want to put back into your blood? How about everything? Water, electrolytes, glucose, amino acids. Okay. What? How are you guys okay with that? We just went through explaining all of those pressures again and all of that to put all of that stuff into the urine. Now we got to do it. Now we got to undo all of that. Why? So think about water. Are you dehydrated right now? I am. All I've had is coffee. So if I'm dehydrated, do I want to reabsorb more or less water? More. But you guys, you're like, no, I'm hydrated. I live a better life than Brian. I wake up on time. Do you need to reabsorb a lot of water? No, probably not as much, right? Same thing with the electrolytes. You don't always need all glucose. You always reabsorb all of your glucose. Sorry, you don't get a say in that. Okay. So again, this allows us to tailor what goes back into the blood. Okay. Tailors what goes back into the blood. So how do we do it? A couple of different things. Sodium is sent via active transport. Sodium is sent via active transport. So a little bit of refresher all the way back to day 1. Holy freaking cow. What does active transport mean?
Requires ATP.
Nice. Requires ATP. Now let's think about, if I spend the energy to reabsorb sodium, what do I get for free? I.e., what follows sodium?
Chloride.
Sure. And?
Water.
Yeah. So yes, chloride, you're not wrong, but takeaway point, there's water. Water is going to be passive, i.e. no ATP. So this is how I kind of think of it. You spend the energy for sodium, you get water for free. So much better than trying to spend 2 energies, 2 ATPs to get 1 of each. Okay. So this is like your BOGO, buy one, get one. Okay. So this slide right here, you don't need to take notes on it, just trying to illustrate a point. As urine moves deeper into the medulla, it gets more concentrated, and then it gets diluted, and then it gets more concentrated again. Why do we have this roller coaster of emotions? Okay, so what I'm trying to say here is, again, you don't need to know these numbers. Look, here's your urine. It's very dilute. At the bottom of the loop of Henle, it's very concentrated. Then it becomes dilute, and then it becomes concentrated again. Why are we going through this crazy trouble of concentrating and diluting and concentrating and diluting? So for reabsorption, step 1, we have active transport. of sodium out of the ascending limb of the loop of Henle. Okay, so in reabsorption, it kind of happens backwards. It's kind of counterintuitive. Urine flows one way, but in order to reabsorb, we need to kind of go backwards. Step one, we actively pump out sodium, i.e., now I'm putting sodium into my blood. If you remember, your blood is just large proteins at this point. So now I have large proteins and sodium in my blood. Am I going to be able to pull a lot of water or a little bit of water?
A lot.
Oh, yes. And that is your step two. Step two, you get passive transport of water out of the descending limb. So with reabsorption, you actively pump out sodium and you get water for free. You actively pump it out in the ascending limb so you can reabsorb it in the descending limb earlier for free. This whole concentrating, diluting, the whole point is kind of this right here, i.e., whole point is to create concentration gradients to reabsorb things. Okay. So what's the whole point of changing the concentrations up and down, up and down? It's so that I have more sodium I can actively pump out. So that way I can actively reabsorb more water. Okay, so takeaway point here for reabsorption, active transport in the ascending limb, passive transport in the descending limb. Okay. Last point I'm going to make, I'm sorry, I know this is bouncing back and forth. It's just easier when you have a picture. Last point I'm going to make here, scrolling all the way up. Remember how I mentioned the PCT, but we've been talking about the loop of Henle? The PCT reabsorbs most things. So i.e., the PCT, that's where the majority of reabsorption happens. That's where we can get our electrolytes, our glucose, our amino acids. What we've been talking about with the reabsorption of water, that's typically at the loop of Henle. Okay, so loop of Henle does 1, PCT does 3. That's why I put the PCT there and not the loop of Henle. Okay. So here's another kind of picture showing that countercurrent multiplier. Again, you don't need to know the numbers, just active at the end, passive in the beginning. Right, and that was reabsorption, not too bad. Again, you don't need to draw this yet, I promise. Just using this as a recap. Now, what we just talked about was reabsorption. Okay, with reabsorption, we're going from which fluid to which fluid?
Urine back into blood.
Urine back into the blood. Okay, and what we just talked about, where does the majority of PCT, or God damn it, Where does the majority of reabsorption happen? Majority is the PCT. Okay, and we're going to be putting it into that peritubular capillary. What are the things we want to reabsorb? What were the 4 things?
Water, electrolytes, amino acids, and glucose.
Nice. Water, electrolytes, amino acids, glucose. Nice work. Okay, so that is the reabsorption there. So again, just nothing too crazy. The thing that we added there was that loop of Henle. Okay, that's to concentrate your urine so you can get some sodium, you can get some water. All right, the last one here, secretion. Secretion, we're going from the urine back into the blood. i.e., we're going, oh, God damn it. No, sorry, it's from the blood to the urine. Ugh. We're going from the peritubular capillary and we're going into the DCT. Okay, if you remember, there's another process that goes from blood to urine. What was that?
Secretion.
Secretion is definitely blood to urine, but what was the other one that goes from blood to urine?
Filtration.
Filtration. 2 processes to go from blood to the urine. What the fuck? Why are we doing this again? Think about your colander. Okay, I want you to imagine you got yourself one of those nice like pre-salad mixes in the bag and they've washed it for you, but hey, wash your stuff. So you dump the bag into your colander, you're mixing around and you find a giant spider in your salad. Is that spider going to go through that colander, through those filtration slits? No. Has anyone ever actually found a spider in their salad? Okay, I have, and that's why I will never, ever buy them again. Just saying. Wash your shit. Okay, so i.e., why do we need to have secretion? Secretion allows us to remove things out of the blood that filtration couldn't. Allows you to remove things out of the blood that filtration couldn't, i.e. that spider. Okay, you remember your glomerulus has those filtration slits. Those limit big things from going through. So what if you need to get rid of big things? The things that you secrete, protons, potassium, these are actually pretty small. But notice they're positively charged. If your glomerulus basement membrane is negatively charged, what happens if you start putting potassium and protons there?
They will adhere. It's attracted to it.
Yeah, they're attracted to it. They're going to stick, and that's going to clog up your glomerulus. That's no good. So we need some other way to get rid of them, hence secretion. NH3, NH4, that is ammonia. Now you guys learned about this. Why do we want to get rid of ammonia? What's so dangerous about ammonia or ammonium ion?
It increases your pH.
It increases your pH. We saw that with hepatic encephalopathy. We need some way to get rid of it, hence secretion. Okay. Ideally, though, we should be getting rid of it via urea. Okay. So here's a nice little review. You guys remember the PCT? What was the main job of the PCT?
Reabsorb water.
Reabsorption,
glucose,
yeah.
all that.
Absolutely. Hey, look at all, oop, I totally missed. Look at all of the things that we can reabsorb. Awesome. Oh shit. That's going the wrong direction. Okay, distal tubule. Hey, look, we are getting rid of stuff like protons and potassium. Cool. Oh shit, we're reabsorbing things too. So have I been lying to you this entire time? Kind of. Filtration only happens in one spot. Reabsorption technically happens throughout the entire nephron, but most of it happens at the PCT. Secretion happens technically throughout the entire nephron, but mostly happens at the DCT. Okay, so just, I'm not going to like test you on this. I'm not going to ask you to memorize what's secreted where. What we wrote down, that's the big idea. Okay. Last thing to note here. So that's the secretion. Last thing to note. Your DCT functions can be changed with hormones. Your DCT's functions can be changed with hormones, i.e., if you're going to secrete hormones to affect your kidneys, it's usually going to change your DCT. Okay, so take for example, I'm in the middle of the desert. I'm trying to find camel urine for whatever reason. I haven't had any water. What should I focus on reabsorbing?
Water.
Yeah. So look, hey, my PCT is reabsorbing water already. Awesome. But I'm going to secrete antidiuretic hormone to help me also reabsorb water at the DCT. So again, if I'm trapped in the desert and I'm dehydrated, this allows me to reabsorb water twice rather than just once with the help of hormones. Okay. So just saying, hey, your DCT, we can change its effects via hormones. All right, so this is what I was leading up to. Now is when you want to pull out your piece of paper, pull out your colors. We're going to do this all on one sheet. Okay. So here's your afferent arterial. Here's your glomerulus. Move. Okay. So first function of the kidneys was right here between the glomerulus and the Bowman's capsule. What was the name of the first function?
Filtration.
Nice. Filtration. And we're going from blood to the urine, i.e., what structures are we moving fluid between?
Glomerulus to the Bowman's capsule.
Nice. Glomerulus to the Bowman's. Okay. Things that we're filtering out, i.e., putting into my urine. Water, glucose, amino acids, and electrolytes. Okay. Step two. Step two was reabsorption. Where did the majority of reabsorption happen?
PCT.
Nice. Where we go from the PCT to the peritubular capillary. Things that we reabsorb water, amino acids, glucose, electrolytes. Then we had the loop of Henle. Didn't really do a true step there. It's not really a true step, so I'm just going to leave it in black. Whole idea is to concentrate the urine. And the final step we just covered, secretion. Final step was secretion. That happened right about here. And we're going from the blood to the urine, from the peritubular capillary to the DCT. Okay. Things we want to secrete: protons, potassium, ammonium ion, urea. Okay. And side note, I'm going to say where hormones act. Voila. You guys see what I'm talking about? This is the meat and potatoes. Okay. So filtration, reabsorption, secretion with a little bit of concentration in there. Okay. So this is what you're going to be responsible for knowing. The other sites with the pictures, there's extra stuff on there. You don't need to worry about that. Cool. Nope, not yet. Cool. Cool. All right. So here, just recapping what we just drew out into painstaking detail: filtration, reabsorption, concentration, secretion. Cool. All right. Now we finally enter the last bit here. We're going to be talking about hormones. Okay. Skip urea for this one. Talking about aldosterone. Aldosterone causes sodium reabsorption and potassium secretion. Now, aldosterone is a hormone. Therefore, which structure does aldosterone work upon?
The DCT.
Perfect. At the DCT. So let's think about this. If I secrete aldosterone, would I make more or less urine?
Less.
So aldosterone causes sodium reabsorption. That means sodium is going from my urine into my blood. What follows sodium?
Water.
Aha. So would I make more or less urine with aldosterone? I'm putting more sodium and water into my blood.
So less.
Yes. So aldosterone would cause you to make less urine. Sorry, did you say less, Ashley?
Yeah, I'm like, what the fuck? Isn't that what I said?
I heard more. Sorry. My bad.
It's like
My bad.
Monday 2.0. It's okay.
It's, yeah, I'm sorry, y'all. I'm struggling. Anti-diuretic hormone. Anti-diuretic hormone. So, hey, diuretic makes you do what?
PP.
PP. So an anti-diuretic makes you not pee. Okay. What anti-diuretic hormone does is it causes water reabsorption, again, at the DCT. So, hey, that's why you don't pee. When you drink alcohol, when you drink ethanol, that causes you to not release anti-diuretic hormone. That inhibits anti-diuretic hormone. So be careful here. This is one of the few double negatives. If we have anti-diuretic hormone, and for whatever reason we have less or an inhibition, if we inhibit anti-diuretic hormone, this is the way I would read this sentence. In the English language, when you have a double negative, they cancel out. So if I inhibit anti-diuretic hormone, what am I going to start doing?
Peeing more.
Peeing more, i.e. alcohol. Alcohol inhibits anti-diuretic hormone. You're going to start peeing more. Okay.
I was told by my one professor in undergrad that that was a myth, but it was like nothing to back it up. I don't remember what class it was even. It wasn't a science class. He just said it was a myth.
I'm going to have to dig that one up.
Okay.
I don't think that one's a myth because I you know, not to brag or anything, but I did used to drink a little bit back in the day, and boy, did God did I pee. It's purely anecdotal. I'll admit that, but I'll have to go figure that one out. Now I'm just thinking about like cracking open a beer just right now to see if I can prove that point. All right. So these two right here, aldosterone, antidiuretic hormone. What does that do to your blood volume? Increase or decrease your blood volume?
Increase.
Increase blood volume. Perfect. Okay. Natriuretic peptide. Natriuretic. You already know what this does. What does natriuretic peptide do?
Does it make you pee out sodium?
Makes you pee out sodium. And if you're peeing out sodium, what else are you peeing out?
Water.
Yep. Awesome. Pee, sodium and water. Diuretics, hey, they make you pee. Therefore, natriuretic peptides and diuretics will decrease blood volume. Cool. All right. So I honestly don't know what this picture is getting at. It's just saying, hey, you can reabsorb water. Cool. All right. You guys are familiar with the RAS pathway. You probably heard about it. Now here we do things a little differently. Okay. So the Rasta actually isn't my invention. It's Trent's. You're going to meet Trent in Q2. He is from Boulder. Hopefully that kind of explains this picture a little bit here, but it's actually his acronym, and it actually works out really well because it describes the entire RAS pathway along with the effects. So how this kind of works, Ra has 4 parts to it, or sorry, 4 A's, but there's an R in there. So part 1, this is the actual pathway. Sta is the effects. Okay, so R is going to stand for renin. R is going to stand for renin. Okay, so renin is released. Actually, let me switch to black so it's just not all red. released by your JG cells. So when we were talking about the juxtaglomerular apparatus, we talked about the JG cells. They cause change. Who detected a problem first, though? What were the other cells? What were the other cells that detected a problem?
Macula densa.
Nice. So this is when you're released by JG cells when your macula densa cells detected hypotension. Okay. So question then, what's the trigger for this whole pathway?
Increased pressure.
Decreased blood pressure. Very good. And what organ do we find the JG cells and the macula densa cells in? What organ, i.e. what organ have we been talking about this entire time?
The kidneys.
Kidneys. Awesome. Next up, we have the first A. This is angiotensinogen. Angiotensinogen. Okay, instantly, what do you know about it?
Creates tension in the capillaries.
Yep. There's a little bit of tension in the capillaries, and that's kind of one of the things that it triggers.
It's inactive.
It's inactive, yeah. It's inactive. Okay. This is going to be a protein made by the liver. Oh God, there's another function of the liver. Look at that. This is constantly circulated. Okay. So right now, you are circulating angiotensinogen. Do you have to worry about that? Not really, because it's inactive. Yeah. Second A, you have angiotensin 1. Now, it seems like this would be active, but it's actually still inactive. So be careful here. Angiotensin 1 is still inactive. This is when renin and angiotensinogen combine in the blood. Okay, so you're constantly circulating angiotensinogen right now. When your blood pressure drops, that's when your kidneys release renin. They meet up and make angiotensin 1. Okay. Still angiotensin 1. You'll hear me call it angio 1. Third A, angiotensin converting enzyme, i.e. ACE. Okay, ACE. This is an enzyme at the lungs, and its job is to convert angio 1 into angio 2. So if anybody keeps up in the news, particularly about the COVID, I don't know why I call it the COVID, about COVID, you might have heard that it actually simulates ACE2, and that's why it does get ferried to the lungs. What we're talking about is ACE1, so not the same thing, but this is why we see such particular problems in people's lungs with COVID is your body thinks that it's one of your hormones that should be in your lungs. I know, and Haley's pug is so cute. I think that's a pug, right? I know, my dog's in it's great. No fun in my house. All good. It helps that I actually know your names and faces now. All right, finally, angiotensin 2. This one now is fully active, and there are systemic effects. Okay, so angio 2, now it's fully active, and now we're going to go on and affect the rest of the body. Okay, so that's the first part of the pathway. Question for you guys. What organs are involved in this pathway?
The kidneys, liver, and lungs.
Lungs and also blood. I.e., holy cow, take a look at this pathway. It requires the whole body. This is a whole body pathway. It takes the whole body for this to actually happen. Okay, and what was the trigger that set this all off?
Hypotension.
Hypotension, nice. Okay, let's get into the 4 effects. S, it's going to be systemic vasoconstriction. Okay, if I systemically vasoconstrict, what does that do to my blood pressure? Yep. Okay. T, this stimulates thirst. You become thirsty. So guess what? You start consuming water. That's going to increase, so let me say increase water consumption. What effect does that have on blood volume? And if you have more blood volume, it increases your blood pressure. Are you guys seeing a trend here? These effects should all be geared towards increasing blood pressure. Why?
Because we were hypotensive.
Because yes, the hypotension is what set everything off. So that makes sense that the 4 effects should be to raise blood pressure. Let's do aldosterone. Okay. Aldosterone. How does that help raise blood pressure? So go back to, what does aldosterone do?
You reabsorb more sodium and water.
You increase sodium reabsorption, thereby you increase water reabsorption. Oh, Lord. Increasing blood volume, increasing blood pressure. Nice. Last one. Antidiuretic hormone. Antidiuretic hormone. That increases water reabsorption, increasing blood volume, increasing blood pressure. Okay. All right. So questions on Rasta. And yes, you do have to say it that way from now on. All right, so your RAS pathway, again, whole body, liver, kidneys, lungs, blood, everything's happening, things are circulating. Okay. Whole body. Okay, and then before the effects of Rasta were to increase blood pressure. Here they're saying increase cardiac output, same thing. Okay, so question for you. If I increase antidiuretic hormone, what does that do to sodium reabsorption? More or less?
More.
Go back to antidiuretic hormone. What does it do?
Reabsorbs water.
So does it have an effect on sodium?
No.
Sorry, trick question. If you secrete antidiuretic hormone, it has no effect on sodium. So actually, let me just do it this way. No effect on sodium reabsorption. But we do see an increase in water reabsorption, increase in blood pressure, or increase in blood volume, increase in blood pressure. What if we do the other side? Natriuretic hormone. It's also called natriuretic peptide. You might see it that way. Natriuretic hormone, natriuretic peptide. What does that do to sodium reabsorption?
Decreases it because you pee it out.
You pee it out. Therefore, water reabsorption goes down, less blood volume, less blood pressure. You're going to learn about this in pharm. Natriuretic hormone, this is an anti-hypertensive medication, i.e. if somebody has high blood pressure, we can give this to them and they pee out their blood volume. Sounds great. We don't use it anymore. Turns out when you give people who are senile medication for them to pee out water in their blood, they sometimes forget if they've taken it or not, or they might double dose. And that can be a lot of big problems. All right. Acidification of urine, i.e. like, hey, your urine has a wide range. So your urine pH is 4.6 to 8.0. Okay, so your urine can range anywhere in that kind of range there. So it can be really acidic or it can be really basic. Why? Think about it does this job with your lungs. Why can your urine be so acidic or so basic?
Would it depend on if you're in respiratory acidosis or alkalosis?
I like that, alkalosis. That's good.
Can't talk
yes.
today. I'm having a hard time.
Oh, I'm in the same boat, yo. So what I'm getting at here is, hey, your kidneys are for acid-base balance. If it's for acid-base balance, remember, it gets rid of the extra stuff. So that's why it can be super acidic or basic. Okay. So that range right there. Okay. Now, ammonia, we've talked about. Let me think about ammonia is converted into urea by which organ? Which organ converts ammonia into urea?
The liver.
The liver. Okay. And then hopefully urea is secreted by which organ? Notice I use the term secreted.
The kidneys?
Specifically, which part of the nephron?
The DCT.
Nice, the DCT. Awesome. Okay. And just recapping, ammonia, highly basic, urea, neutral. Okay. However, urea is only temporary. Okay. Hormones, we kind of talked about, kind of. That's your natriuretic peptide, natriuretic hormone. Okay. Vitamin D, don't worry about. Didn't really talk about it. EPO, oh boy, EPO. Released with decreased oxygen. Okay. And then renin. When is renin released?
Low blood pressure.
Nice. Low blood pressure. Both EPO and renin come from which cells?
Macula densa.
They detect
Oh.
change.
I don't know, JC cells.
Yeah, JG cells. That's why I just say JG cells. Very good. Okay. All right. Last big push here. We're talking a little bit about tests, renal tests. Okay. You're going to learn much more about these in Foundations and MedSurg 1. This is just kind of an overview to help you kind of understand the logic behind these tests. Okay. So when we want to measure glomerular filtration rate, i.e. we want to measure GFR. Okay. First off, your glomerular filtration rate, that's at your glomerulus. We're measuring how much water your glomerulus is moving. We look at creatinine. Now be careful, this is not creatine, this is creatinine. Okay. Creatinine is a byproduct of protein metabolism. Okay. Now, this is a reflection of protein metabolism, i.e., do you have a widely fluctuating metabolism? Does your metabolism change throughout really the day? Not really. So, i.e., this should be a constant. This is constantly being filtered. It's constantly being filtered, i.e., you're constantly filtering the same amount at all times throughout the day. So what I'm getting at is creatinine, should be in the urine. And you make a consistent amount. So 2 ways to look at this is we can look at creatinine in the urine. If we look at creatinine in the urine, okay, if you have high levels of creatinine, stupid high levels of creatinine, what would that kind of indicate to you? So kind of think of it this way. You have your colander, you have your kale, you turn on the water, but even more water dumps out into the sink. That's weird. What could be wrong? Like, you turn on the sink, it should like kind of disperse the water evenly. You turn on the sink and just it goes right through to the sink. What did that tell you about your colander?
It's busted.
It's probably busted. So if you see high levels of creatinine in the urine, that means your colander probably has a giant hole in it. Things are leaking out too quickly. So this might indicate glomerular damage. Now, what if you have low creatinine in the urine, i.e. you turn on the sink and you get a couple drops of water. That's it.
Maybe your afferent arteriole is constricted. Blocked.
Yeah, nice. Maybe your afferent arteriole is constricted, i.e. there's no blood, there's no urine. Very good. This can indicate some sort of, this can indicate, I'm going to say, some renal obstruction. We have a blockage somewhere. It could be in the afferent arteriole. It could be maybe in the renal pelvis, something, but either way, you don't see any creatinine in the urine, something is blocked. Something has blocked your colander. Okay. Now, the thing about creatinine is this is the best measure for GFR because it allows us to directly look at your colander. However, this takes 24 hours. That means if I want to determine your creatinine clearance, I need to collect your urine over 24 hours and build a curve. I need to know what your normal is. In emergency medicine, do you always have 24 hours? So sometimes we need something a little bit quicker, hence the blood tests. The blood tests are quicker, but not as specific. Okay, so two things that we can look at in the blood. Plasma creatinine. So be careful here, guys. If I say creatinine by itself, that's referring to creatinine in the urine. If I talk about plasma creatinine, that's creatinine in the blood. Okay. So be careful there. Now, if I have high levels of creatinine in the blood, what does that indicate? It should be constantly going into my urine. I take somebody's blood and it is super high. What might be going on?
A renal obstruction.
Maybe a renal obstruction. Maybe there's not enough blood flow. You see what I'm talking about? Is it's not very specific. Is it a problem with the blood flow? Is it a problem with the urine flow? Is it a problem with the kidneys? Maybe it's a problem with the liver. Okay, so if we have elevated creatinine in the blood, all we know is that we are not filtering. All we know is we are not filtering. Is it because I don't have anything to filter? Is it that I'm clogged? Is it that blood's not even going to my kidney? Who knows? What if you see low creatinine in the blood? What if you see low creatinine in the blood? Again, it should be in your urine. So if you see low levels of creatinine in the blood, what might that indicate?
Filtering too much.
That's like if you see absolutely none, maybe. So, i.e., should your creatinine levels be high or low in your blood? Should be low, i.e., this is normal. You're filtering it. That means it's not building up in your blood. Awesome. Another thing that we can look at is BUN. Now, guys, I'm going to give you a heads up here. I get in trouble for this one. It's supposed to be pronounced BUN, and apparently I've been corrected by several faculty at this point. I have always heard it called bun, and I call it bun. So if you call it bun, do not blame me, please. But just heads up, it's probably called BUN, but I'm just going to call it bun because it's easier. Okay. So if we're looking at them buns, hun, we're looking at urea nitrogen, i.e., we're looking at urea in the blood. We're looking at urea in the blood. Okay, if you have high levels of urea in the blood, what does that indicate? What should you be doing with urea?
Peeing it out.
You should be peeing it out. How? Filtration, reabsorption, or secretion?
Secretion.
It should be secretion. So maybe we are not secreting. Okay, so it could be a kidney problem, or it could be that I have gout. Maybe I just produce more urea than an average person. You guys get what I'm saying here with these blood tests? They're great, they're a quick answer, but they're not very specific. And if you have low levels of urea in your blood, good, bad, normal, explosions?
Normal.
Yeah, you shouldn't have a lot of urea in your blood. It's typically normal. Awesome. Okay, again, I'm not going to be looking for like crazy specifics here. I'm not going to give you crazy numbers. I just need you to know the logic behind creatinine constantly being put into the urine at a constant rate. Best if we can measure the urine over 24 hours. If not, what does it mean if creatinine or urea is building up in the blood? Okay. Final question. Why are black toilets a bad idea?
I don't know, but I feel like it's going to be a dad joke.
No, there's an actual nursing application behind it. Jeez.
I guess, I don't know, you can't see the color of your poop.
Yeah, you can't see the color of your pee, your poo. Exactly. You don't know if you're peeing blood. And they're just really tacky. They're just terribly tacky. And I don't know if you guys live with any dudes, but if you think our aim is bad in the dark and you want us shooting into a black toilet, it ain't happening. Have a great break, y'all. Thanks for hanging in there.